Welcome to Professor Mad. We mainly have two current types that are widely used. One is alternating current, which periodically reverses direction. And other is direct current, which flows in only one direction. Our homes get alternating current from the grid, but most of the modern electronics equipments are using direct current. So we need to convert the AC to DC. This process of converting alternating current into direct current is given the name rectification. Let's discuss how to convert 230 AC into desired DC value. In this video, we are describing a traditional transformer-based design. For the ease of understand, hope we are going to convert 230 V AC into 12 V DC. It consists of 4 simple steps. 1. Stepping down the voltage levels. 2. AC to DC power converter circuit. 3. Obtaining pure DC from pulsating DC. 4. Regulating DC voltage. Let's discuss one by one. First of all, using a step-down transformer, the available 230 V AC power supply should be converted into lower voltage, only the magnitude of the voltage is changed. Next, this low voltage should be converted to DC. For that we are using AC to DC converter circuit. Converting alternating current into direct current is given the name rectification. A PN junction diode conducts current only in one direction. The same principle is made use of in rectifier to convert AC to DC. When the diode is at forward bias, current flow through the circuit. Let's try to reverse the polarity and see what happens. Here the diode is reverse biased, then the current can't go through it. Let's replace the battery by AC power source. It frequently reverses the direction like this. When AC power is applied to a common incandescent lamp, it turns on and off repeatedly like this, but this happens so fast that we can't see the possess. Let's see what happened after adding a diode into the circuit. As you can see, diodes only allow current to pass through when it is forward biased. When the AC voltage is positive on the cathode side of the diode allows the current to pass through to the output. But when the AC current reverses direction and becomes negative on the cathode side of the diode blocks the current so that no voltage appears at the output. So in the circuit, current is only flowing through in one direction. Let's graph the current on both circuits. You can see that only the half of the input wave is passed through the diode, so it is called half-wave rectifier. Half-wave rectifiers are simple enough to build but aren't very efficient. That's because the entire negative cycle of the AC input is blocked by a half-wave rectifier. As a result, output voltage is 0 half of the time. So the full-wave rectifier is needed. There are two major types of full-wave rectifier designs used frequently. The smaller design uses 2 diodes. If the transformer is center tapped, then 2 diodes back-to-back can form a full-wave rectifier. It converts both the positive and negative halves of the input waveform to a single polarity, positive or negative, at its output. By using both halves of the AC waveform, full-wave rectification is more efficient than half-wave. When a simple transformer without a center tapped secondary is used, 4 diodes are required, instead of the one needed for half-wave rectification. It called bridge rectifier. This 4-diode configuration is called diode bridge circuit. Now we have rectified full wave, but the problem is voltage is not stable. The output across the diodes in the above steps is neither complete nor is it completely DC. The output is not steady DC and is not practical to use with circuits. Let's talk about how to obtain a pure DC from pulsating DC. This is called filtering or smoothing the rectified voltage. A filter circuit, also known as a smoothing capacitor, is added to the rectifier circuit to improve the output. The smoothing capacitor converts the rippled output of the rectifier into a smoother DC output. Capacitor charges up when the voltage levels increase, and it releases the stored charges when the voltage level decreases. Even though the output is smooth, there are little residual periodic variations. Now we know the basic 3 steps of the AC to DC conversion process. By combining all these steps we can make AC to DC converter like this. But still our DC output signal has slight variations, we call this ripples. If we want to smooth it furthermore and regulate voltage at a constant level, we can use a voltage regulator IC. It's basically a 3-pin IC. This is the final step of the AC to DC conversion process. We can summarize all of the above steps to one. The waveforms of each stage are like this. Finally we have our 230V AC to 12V pure DC converter circuit. Hope this video helps you. Like and subscribe us for more educational videos.